Greetings. Welcome to our discussion of cloud connectivity for medical devices. I hope you've had your coffee because we will be covering quite a bit of ground in a short time. By the end of this talk, I hope you'll feel much more comfortable with integrating your medical devices with the cloud. A little bit about myself. My name is Dana Good, and I've been a software engineer for a long time. I've worked for about 16 years in systems, embedded, and medical device software, including several Class 3 devices. Over the last 6 years, I have worked on several cloud-connected projects, and I hope to share some of what I've learned with you today. I work for Stratos Product Development in Seattle. We are a full-service consultancy creating devices for our clients, and many of these are medical devices. We have engineering expertise across many disciplines. Most of our engineers are quite senior. These are a few of our clients over the last 25 years. So let's get down to business. The presentation has one goal: to lay out what goes into building a connected medical device system and how to avoid some of the problems that might occur. Here's how we'll spend our time. First, we'll take a few minutes to talk about cloud services and what they have to offer. Then, in the next section, we'll look in more detail at some of the challenges involved in creating this type of system, and we'll go through how to solve those challenges. What I want to present, and what I hope you adopt, is a successful high-level approach to creating a solid cloud-connected system. Let's get started with the content of the presentation. In this first section, we'll take a look at what the cloud is and is not. In case you're brand new to cloud computing, connecting to the cloud means using or writing software that connects to a set of cloud services. These services are controlled by the cloud services provider, and they leverage software and hardware that could be hosted just about anywhere. Let's start with some history. Way back in the early 2000s, Amazon, Microsoft, and a few other providers all began to offer cloud services, many of which were commercialized versions of their own internal distributed systems. The early cloud offerings were as different as the organizations providing them. Interoperability, best practices, regulatory guidelines, these barely existed. Security, authentication, and access controls in the cloud were spotty at best. This meant that early systems took a long time to build and often had significant shortcomings. I thought about what architectural diagram to show in this slide, but really, this picture about sums it up. Back then, every system was different and you were pretty much on your own. In the time since, cloud services have come a long way, and now there is a clear architectural paradigm. Let's talk about what the different layers of this cloud pyramid have to offer. Starting from the top layer, we have SaaS. Software as a service provides complete distributed software solutions like LinkedIn, Dropbox, or Facebook. Examples of medical SaaS solutions include a front office medical record system or even an analytics dashboard. All SaaS systems are end-user systems. They have cloud-based underpinnings. PaaS, Platform as a Service, offers software capabilities through its software APIs, including domain-specific business logic and support for non-functional attributes like security, privacy, availability, and performance. Quite a lot of consumer systems are built on top of PaaS offerings. For instance, a music streaming service might simply build its application over a PaaS resource that manages everything, including uploading, downloading, and streaming of media, as well as customer records and a music storefront. And finally, we come to infrastructure as a service, also known as IaaS, which provides access to hardware and computing resources like virtual machines, storage, networks, and message queues. This level gives you deep control over configuring and monitoring cloud resources. Now that these service layers are well documented and developed, cloud services have really come a long way, which is great because otherwise you couldn't consider them for use in your medical device system. So it seems we have arrived. Your company has years or maybe even decades of medical device experience. We've seen 10 solid years of cloud services development. You can combine these things. You've got this, right? Cloud service providers will tell you that you can create a cloud system in 3 hours. And they're right, you can. But will it be the system that you need? Maybe not. So let's take a closer look at the cloud services model. I'm sure you already knew this. Doing it right is going to be hard. We've come a long way, but the task is still non-trivial. Here's another view of cloud services that breaks down responsibilities in a helpful way. This diagram gives you a sense of how responsibility shifts from vendor to developer as you move down the cloud services pyramid. The right-hand column represents the top of the pyramid. You can see that the SaaS users manage nothing. They simply use a connected application. They are your product's customers. Moving left from this column, Platform as a Service users are application developers. They will add a layer of functionality and user interface over this infrastructure and business logic that's underneath. Finally, a system that uses IaaS directly is likely to be complex. IaaS developers manage the services shown in blue. They will create a customized system-level architecture and implementation. And here's what's not always obvious. Whether you use IaaS or PaaS to implement your system, or a combination of the two, your product will ultimately contain one or more SaaS applications. In other words, though as developers you are cloud services users, as an organization you will be a cloud services vendor. As a vendor, your organization becomes responsible for the entire system beneath it. To ensure that your system meets all of your requirements and your regulatory obligations, you will need to partner with your cloud services provider to understand the layers below your implementation. So, first thing to remember, your cloud services provider must be part of your team from the beginning. Okay, there will be challenges, but let's put aside these concerns for a few minutes and look at the upside, focusing on the value that cloud systems can provide. As you know, a robust cloud solution can make sure that your medical data is protected, private, and available 24/7 from multiple locations. Cloud systems are not just designed to accept and return data. A cloud system can actively monitor, manage, and upgrade your medical devices in the field. And if you provide PaaS and SaaS interfaces at your own organization, you can support collaborative efforts with partners in research studies, clinical trials, and data analytics. These are just a few ideas. You'll have many more at your organizations. Cloud services really can help make these a reality. We've taken a look at the state of cloud services now. Now let's talk about what is needed to build a robust cloud-connected medical device system. When you move into the cloud, the problem you need to solve expands in several different dimensions. This talk can't possibly address every challenge that might come up, but I hope that addressing some specific pitfalls will help to shine a bright light on the approach that we recommend. With that in mind, let's look at a few of the ways that things can go sideways and how to head off trouble before it begins. Serious flaws can occur in even the simplest cloud-connected system, so I've put together an example of a simple connected medical monitoring system for us to consider. Here's a very simple diagram of a cloud-connected patient monitoring system. Patient data is uploaded to the cloud. Analysis tasks run and store their results in the cloud. Staff and care providers can retrieve data and analytics to their mobile devices. I'll keep this slide up for a moment while I describe the system in more detail, so you can think about the challenges the system faces and some of the things you think might need to be addressed. The components of this monitoring system include an existing commercial point-of-care patient monitor, a new RESTful interface over Wi-Fi to a cloud front end, a POS offering upload, storage, analytics, and data retrieval capabilities, access to patient monitoring and analytics results from apps on mobile devices. The system will need to offer high measures of performance, 24/7 availability, and high reliability across several regions in the United States. This is a simple system now, but the company has big dreams. They know that the cloud can send information in both directions, and their plan is for their next monitoring device to provide a real-time video window for remote caregiver consultation. They also want the system to support over-the-air software updates and remote configuration. The cloud service provider will provide the software APIs as well as the software and hardware infrastructure. Monitoring Systems, Inc. is responsible for developing the monitor-to-cloud and cloud-to-device interfaces and the mobile apps, for integrating the system, and for supporting the system after deployment. You may want to pause here to think about some of the challenges this system may face. And now let's continue and see what happens with the new system. The monitoring system is built on a platform as a service, with a focus on medical device systems. Development was therefore quick, and now the system has been released to quality engineering. 2 weeks before the expected launch, the quality group delivers some bad news. It turns out the system is vulnerable to packet sniffing between the patient monitor and the cloud. Since patient data was neither de-identified nor encrypted during transport, both personally identifiable information and protected health information are readable in clear text. Furthermore, when the quality team digs in deeper, they find that the open nature of the interface makes the system susceptible to a man-in-the-middle attack. And it turns out that Monitoring Systems, Inc. made the mistake of connecting their device directly to the cloud over the internet using a Wi-Fi connection. Adding encryption and de-identification to the medical device software now will require non-trivial changes to the system's requirements, risk control, and verification test documents, not to mention its software design documents and unit test suite. All of this must be followed by re-verification. Project rollout comes to a standstill while the development team studies how to retrofit an encryption and de-identification approach into its cloud interface. This is not simple or quick. We all know how much longer a retrofit takes than a solution designed in from the start. Eventually, the company makes the decision to revert their device software to the previous version, and it builds a PC application which connects the patient monitor to the cloud. The new PC application has fewer regulatory requirements. Its input is the output of the monitor's original software. The PC provides native 128 and 256-bit encryption and plenty of horsepower to cache and de-identify data before uploading it. It is generally a strong solution. But there has been a 4-month delay in deploying the modified system, and something else also happened. Because the team was backed into a corner and changed to a wired PC connection, the mobility and usability of the monitor has been compromised. This team learns that for many reasons, designing a software or a device layer between the medical device and the cloud is a best practice. So how could the problems we just saw with the monitoring system have been avoided? First, it turns out It's not realistic to expect even senior developers to be expert in all aspects of a cloud-connected medical system. So it's important to start your phase zero by putting the right team in place. You want to build and involve your team at the start to help create the system requirements. Of course, you know that there will be development and quality engineers on that team, but there are other team members your project can't do without. Let's start with IT. IT experts can provide important advice and support for security and privacy on this topic. It's right in their wheelhouse, since many IT services have already taken proprietary data off premises into the cloud. Of course, regulatory partners on the team would also naturally be concerned with security and privacy. I mentioned best practices in the last slide. Industry and standards organizations have created excellent lists of cloud best practices, representing the combined experiences of more than 10 years of success and failure. The importance of these lists can't be overstated, and I have included links to some of them at the end of this presentation. If monitoring systems had adopted best practices early on, they would have avoided these security and privacy issues. And speaking of best practices, here's one we haven't mentioned yet: a deep cross-disciplinary design review. This kind of design review likely would have identified the missing layer between the cloud and external devices and might have avoided the last resort wired-in PC system. So the company adds IT to its team, and something good happens. When IT talks with the cloud services provider, they discover that data which is stored by the POS in the cloud is only encrypted if it has been explicitly configured that way. You would think this would be the default, but you can't really assume anything if you want to be safe. Fortunately, this is a simple configuration change. Accomplishing it is a big win for the system. With IT on board and security vulnerabilities addressed, 4 months later, the system is rolled out for the first time. April 1st, 2017, the system is rolled out. It's broadly adopted, and it's a clear success. A month after system rollout, the company begins to hear some bad news about its performance. Physicians are complaining that data uploads are taking minutes instead of seconds, and downloads to mobile devices are taking 5 to 10 times as long as they were just a month earlier. The monitoring system's performance goals are failing. Adoption and use are overwhelming the system. So what does it take to keep a cloud system performant? Let's start with auto-scaling. Auto-scaling is the ability of the system to respond dynamically to load by launching additional worker nodes to keep system response steady. To explain this graphically, I'm going to introduce one of Amazon's AWS reference architectural diagrams, because it is very descriptive, if a little busy. Here's an AWS architectural diagram for a typical batch processing system, showing auto-scaling. The job manager directs data to the job data store, stores a record in the database describing the data, and alerts the worker nodes to new analytics requests. The worker nodes scale up and down as needed. This is at the heart of the cloud concept. But in this case, the POS system used by the connected patient monitor already provides auto-scaling for its worker nodes. So why did the system response deteriorate? Consider what happens when the front-end job manager itself becomes overloaded. If there's anything certain in cloud systems, it's that what you think will never happen will always happen, sooner or later, and this is no exception. This type of overloading can happen for many reasons. During recovery from a regional power failure, for instance, many devices can come back online simultaneously. The development team looks into the problem and finds that their platform as a service solution is missing an important architectural element, load balancing, which addresses overloading at the front end of a system. Load balancing, which we'll look at next, is another cloud best practice. So, for an I/O-heavy system like the monitoring system, it would be more appropriate to start with something like a media sharing architecture. In this diagram, the dark areas represent input to the system, and the light areas represent output. The hexagonal icons are load balancers, which are tracking and managing load across multiple identical subsystems. When a load balancing service is used, data is routed away from the compute clusters that are overloaded and towards those which still have capacity. Back to the performance problem in the monitoring system, the POS for this system doesn't offer load balancing at all. So the performance bottleneck can't be fixed without switching POS providers. It's painful to realize that the solution was available from a different POS provider with minimal impact. Instead, this system will continue to struggle with performance issues. We just saw how performance tanked when the job manager became overloaded and how load balancing is part of addressing performance. But the larger problem here was that the need for load balancing was not detected until after the system was deployed. Wouldn't it have been better to have avoided this situation entirely? This is another case where following best practices would have led to a more solid architecture. If the system's required throughput had been characterized early on, if the system had been designed for peak loads, if real load tests had been run, it's very likely that the need for load balancing would have been identified up front. Of course, it's possible for any system to eventually outgrow its design. That's why best practices mandate a design that includes automated system monitors and reporting, the creation of system load metrics, history, and statistics, so that the software can be updated to keep pace with growth. In other words, you need eyes and ears inside the cloud. You never want to be flying blind. So where are we now? We've looked at a couple of different scenarios and gotten a taste of a few things that can go wrong. I'm hoping that the main themes of adopting best practices and building a team early on are starting to come through. Before we leave the patient monitoring system behind for good, here's one more scenario to consider. 4 months after system rollout, a hurricane takes out power on the East Coast. This happens to be the area where the monitoring system's POS is deployed. The cloud connection goes down, and healthcare providers across the United States begin frantically using flash drives to manually retrieve patient information from their monitoring systems. Let's take a look at what went wrong here. The layers in this pyramid may look abstract, but each is running on physical hardware in real geographic locations. Your system relies on this infrastructure, and it will not always work. In fact, at any time it's guaranteed that only part of your service provider's infrastructure will be working. That is why you must design to fail. As you probably know, cloud systems that are designed to fail offer higher reliability than even traditional distributed systems. Fault tolerance is how you leverage all those cloud resources to create a stronger system. This is also how Netflix survived a major cloud services outage in 2011, although many other services went down. Its systems continued to run on different hardware in different regions, and their system did not go down. So, what will your strategy be for failover? For a conventional medical device, that question might not make sense, but for a cloud system, it is essential. Since YOS hardware is broadly distributed across geographical areas, most YOS and POS providers offer services that detect failures in one region and redirect traffic to another. These are sometimes called DNS failover solutions, and they're crucial to a highly available system. Since there's no failover strategy for this connected patient monitoring system, what can be done to address the system outage? 4 months after release, the development team is no longer available. Well, this problem requires the final component of the product team, the DevOps group. DevOps is charged with deploying, monitoring, reporting on, and maintaining a cloud system. Fortunately, Monitoring Systems Inc. did add a DevOps team just before rollout, and they are called in at midnight. By 4 a.m. through heroic effort, they have redeployed the system to infrastructure on the West Coast, and it's running again. So who should take responsibility for this outage? Even though it might seem that the POS provider is responsible, their service level agreement in this case tells a different story. The SLA is a contract that lays out the system attributes that are the responsibility of your cloud services provider. And since failover support was not included in the SLA by this provider, it's not likely to be available to the system. Just to spell it out, this is something the development team should have considered ahead of time. And had DevOps been part of the team from the start, they probably would have. Though it might be tempting to add DevOps late in the project, remember that cloud systems are not launch and leave software. Your DevOps team will support your cloud-connected medical device system as long as it is deployed. If you bring them in early, they will provide crucial insights and requirements in support of deploying, monitoring, and controlling your solution. This wraps up our discussion of the example patient monitoring system. Let's review some of the things that we've covered. And before we review these best practices, I want to say that we have only touched on a small number of ways that cloud-based challenges can affect this project, or any cloud-connected project. Building a really solid system requires a coherent approach to proactively identifying and addressing design risks that goes beyond a small set of learning points. We'll address this after the review as we wrap up the presentation. Let's look back over some of the best practices that we've talked about today. Remember to protect your data at all times while moving to the cloud, from the cloud, and while it is in the cloud. Provide scalability and load balancing to keep your system performant. Design for failure. This can take many different forms. Deployment strategies that we haven't talked about yet include configuration, rollout and rollback, and bug fixes. Become familiar early on with what your cloud services provider has to offer and what their limitations are. And put your team together early on and use them well. These best practices are crucial, and yet by themselves they are not enough. I hope you leave here with something more important than a small set of best practices. I want you to leave with a method for successfully approaching a cloud-connected medical device project. That's what we've been aiming for all along, and it looks like this. Feel free to forget everything else I said, as long as you remember these things. First, build your team and ensure that every team member contributes to the system requirements and reviews the design. Second, identify and adopt the best practices that apply to your project. Those best practices will direct your team efforts for the duration of the project. Finally, spend your time up front. Architect and design for robustness and for your testing until you are very sure. The proof will be in the result. As you know, development flows more quickly once you have a well-architected design, and retrofitting a live system is not something you will want to do. To sum up, I will just restate this one last time. Engineers don't need to be experts in security or regulatory requirements to be successful in building a solid, cloud-connected medical device system, as long as they are part of a strong team that adopts and follows established best practices. Finally, here is a set of resources you may wish to investigate as you look into building your cloud-connected system.